We'll continue our work here on Chapter 35, the reflection of light in lenses. The next section is section 35.3, where we look at farsightedness and nearsightedness of the human eye, as well as aberrations. Farsightedness, or hyperopic conditions, need a converging lens, as I will show you here. If we think about a point out here, and we have an object right here, and a human eye over here with the lens in the front, then the light from this object goes in here to the lens, but rather than focusing back here where it should focus, it actually focuses at a point to the rear. And what we need then is a converging lens to the front, which normally would probably look like this. And when we put that converging lens in, then what we see is, as the light goes in, I'll use dots this time, it will then focus correctly on the back of the eye, where the sensors are that take this image to the brain and not have it unfocused. Similarly, a myoptic condition, or nearsightedness, needs to use a diverging lens. And for that, we might have an object here, and the human eye here. And normally what happens is the light comes in from the object, goes through the lens of the eye, and focuses too soon, so that it focuses here. Therefore you have a fuzzy image back here, or blurred image. And what we need here is a diverging lens. And if we have the diverging lens, then we will have more like this, where it doesn't focus quite as rapidly. Of course, the lens has to go up here, and it will actually come back and focus correctly on the rear of the eye, where the sensors are. So this is farsightedness. This is nearsighted. Next, I want to look at lenses in combination. If we look at lenses in combination with one another, we might have an object that's over here, and let's say a converging lens right here. And as the light goes through this converging lens, converging to a point here where we would see an image here. This is an object, and here is an image. And if we put a piece of paper here, or a screen, then we'd be able to see a clear view of the image of this object. However, if we put a second lens here, using therefore a combination of the two, then the light from this image will go here to this lens and be focused to the eye. Here's the eye back here again, and go into the eye. And the image that we would have from these two converging lenses would be more like the image was out here, and it would be inverted. So we get a large degree of magnification. So we can say that the first lens forms an image, which is then used as an object for the second lens, which then focuses that image object into a new image within the eye, so that it appears to be back here and is greatly magnified. This would be an example of a compound microscope. And it gives us an idea of how lenses function in conjunction with one another. Now, the last topic that I want to discuss here under section 35.3 is the concept of aberrations. If we look at a lens, there are two types of normal aberrations that we have. And by an aberration, we mean something that's abnormal. If we take an object out here and look at how that light is focused, to make an image here, object, it turns out that the easiest lens to make is what we call a spherical surface. This has a radius of curvature back here, and it's as though this is part of a sphere. These are much easier to make and much less expensive, and this will be the surface of a sphere. So these are circular in nature, meaning that all of these points point back to a certain radius. Now, when you have a lens that's made with such circular design for the surfaces of the lens, it turns out that when we take an object and focus it at a point, not all of the rays will focus at the same place. In fact, this part of the object might focus here, and another part of the object might focus in another position. So in fact, what we have is a fuzziness associated with the image, because each part of the object at different distances from the center will focus at different positions here. So when we put up a flat plane, then in fact we do not get an exact focus of the image. This is called spherical aberration. Spherical aberration refers to the fact that the aberration or abnormality in the focusing of the light is due to the spherical surfaces. Then there's a second type of aberration, chromatic aberration. Here we get the same type of thing, but even from the same point here, it may focus here for red light, and for blue light it would focus back here. That means that there's no way to make a color image where all of the colors are focusing at the same place. This is called chromatic, for chromo for color. Chromatic aberration. Now you would think it'd be easy to design by computers a lens that would correct both the spherical aberration and the chromatic aberration, because we want the light to focus at the given point for film or for charge coupled devices to pick up this image digitally, and we want all colors to focus at the same place at the same time. Not just green light all focusing in the same plane, but every color, all of them focusing no matter what the distance out. It turns out that's extremely difficult to manufacture. It is much easier using computers to compound lenses, taking one and then another, then another, then another, and to make up a compound lens made actually of several lenses, and this can be designed to optimally, in terms of cost, correct both spherical and chromatic aberration. Of course, this is more expensive. Therefore, when you have a camera that uses a more expensive type of lens, you have better correction of both the spherical and the chromatic aberration.